Dear students, welcome to this lecture of Digital Logic and System Design. Today we are going to discuss another method of simplifying a given Boolean expression to its minimal form. See, the one that we have already discussed, in fact, we have discussed two. One is the Boolean logic or the postulates, the Huntington postulates and the Boolean theorems based method that we already discussed. The other one was the Carnot's maps. We have seen that Carnot's maps, they are pretty convenient when the number of variables is up to 4, 2, 3, 4, that we have seen. But when it goes beyond 4, it starts getting very difficult. 5, 6, we have seen, it becomes very difficult to visualize the combination of the various min terms in order to get the minimized function. So that is why we must study another method which is equally convenient, I would say, regardless of the number of variables. If the number of variables are 2 or 3 or 4 or 5 or 6 or even beyond 7, 8, 9, 10, you go on adding the number of variables, but the method remains the same. It is only that the length of the method will obviously increase when the number of variables increase. So that method is the tabulation method. It is also called Quine-McCluskey method, based on the person who proposed Quine, and then there was some modification suggested by McCluskey. So it may alternately be called Quine-McCluskey method, but as a common name we call it a tabulation method. So let us take an example and see. Suppose we are given this function in sum of product form. So obviously from here we can make out that this must be a 4 variable function because our min terms are going up till 15 only. There is no min term beyond 15. So we can assume that the number of variables here are 4, right? So I have to minimize this function. So I'll use tabulation method. How to do it using K-map? That we already know. We'll have to have a 4 variable K-map in order to minimize. So that we have practiced and we have seen already. Let us see how do we do it using tabulation method. The first step in the tabulation method is to group these min terms as per the number of ones in it. For example, the very first min term 0, when I do the binary representation, it has no 1 in it. There is not a single 1 in it. So this will form one group. The next group should have all such min terms which have just one 1 in it, just a single 1 in it. What are they? 1 is such, 2 is the other one, and 8 is the third one that I can make out from here. It will be a useful practice if, as you start grouping these min terms as per the number of ones in them, you keep on clicking them or ticking them also. Like 0 has been done, so you tick it here. Similarly, 1 to 8, it is just a coincidence that they are taken in a sequence. They are coming in a sequence in the same group. Otherwise, you keep ticking them. Now you see over here, 10 is such a min term which has two ones in it. So that will form the third group. It is 1010, so two ones in it. So it will form the third group. Then 11, 14, they will form the next group because they have three ones in them. And 15 will form the last group which will have all four ones in it. We are talking about four variables. So the maximum ones we can have are four ones in it, right? So to begin with, we have taken an easy example where the sequence itself was such that they may be grouped in as per the number of ones in each of those min terms, right? We'll take also the examples where they may not necessarily be sequenced according to the number of ones in them. But as of now, the first step is to group them as per the number of ones in each of those min terms binary representation. Now, first step completed. Second step is we will take adjacent groups and we will take all the possible pairs in each of the adjacent groups to see whether the variation is in a single place. For example, I can combine 0 and 1. Why? Because three bits are common, three bits are the same. This is this bit which is varying. So what I'll do is I'll write 0 1 because they are combining, and I'll say 0 0 0 dash. Dash means it has been eliminated. Z has been eliminated, whereas W, X, Y, they're all constant and they are kept as 0 0 0. And also again you tick both of them because they have been covered, right? Next combination is 0 2. They can also be combined. So this has already been ticked, so no need to tick it again, but this must be ticked because this is a new number which has not been ticked so far. And now I'll write here 0 2, and then I can write 0 0, and since this is varying, so I'll write 0 0 dash 0, right? 0 0 0 dash 0. So this is what I'll do. 0 2 can be combined and I'll write 0 0 dash 0. Then I'll take 0 8. They can also be combined. So I'll tick 8 as well. 0 had been ticked already, so I'll tick 8 again. There's no need to keep on ticking every time it combines. Only once is good enough. So when I combine these two, I can write 0 8 can be combined because they are varying in just a single bit. So it will be dash because this is varying, and then 0 0 0. So I'll write dash 0 0 0. So that pretty much takes care of these two groups and their combination. The next I'm going to see I'll draw a line here. Just as I've been drawing lines after every group in the first step, I'll draw a line here as well after every combination, right? So I'll draw a line here. Next, I'm going to see the combination of this group with this group. I am seeing only with the adjacent groups. I won't see with this the combination of this group with this group because this group is having just a single one and this is having two ones. So there is no way that the variation may be in a single bit because the number of ones itself are different. So obviously it will vary in more than one place. So there's no point in considering groups which are not adjacent to each other. So let us consider these two groups. So combination of 1 and 10 cannot be done. Why? Because they are varying in more than one place. I can make out from here itself. This is 1 0 and this is 0 1. So even if I consider the other places, it is varying in more than one place. So they cannot be combined. So that is why I haven't written 1 and 10 here. And I have not ticked 10 so far. I'll not tick 10 so far because it has not been combined. 1 has been ticked because it combined with the earlier one. So that will remain ticked. The next combination will be that of 210. Now I see that 210 can be combined because this is not varying, this is not varying, this is not varying, but this bit which is MSB is varying. So what I'll write? Now I'll say 210, they can be combined, and now I'll tick 10 because 210 has combined, so I'll tick 10. And then I'll write this is varying, so dash 0 1 0. So it will be dash 0 1 0 with the combination of 210 being done. Similarly, 8 10 can also be combined. So if any one of them have not been ticked so far, I'll tick them. In fact, they have been ticked before, so no need to keep on ticking so many times. So 8 10, I'll say 8 10, they can be combined. And what will be it? 1 0 dash 0, because this is the only place where it is varying. So 1 0 dash 0. So 8 10 1 0 dash 0. So all the possible combinations in these two adjacent groups have been taken care of. Now I'll come to these two adjacent groups, right? So when I see 10 11, yes, they can be combined because they are varying in a single bit. So I'll tick 10 and 11 provided that they have not been ticked before. So 10 11 I'll write, and what will I write here? I'll say 1 0 1 dash because this is varying, so a dash here, this has been eliminated. So I'll say 1 0 1 dash. So 10 11 can be combined. Next combination will be that of 10 14. They can also be combined because they are varying in this particular bit. Rest of the bits are the same. So I'll tick again 10 14 if they've not been ticked so far, and then I'll write the combination 10 14. And what will I write here? I'll write 1 dash 1 0. Whatever is constant, I'll copy it like this, and whatever is varying, I'll place a dash here. So I'll say 1 dash 1 0, 1 dash 1 0. So that covers all the combinations in these two adjacent groups. Now over here, let us see. 11 15 can be combined. Tick them if they have not been ticked so far. Write 11 15 here, and it will be 1 dash 1 1. So 1 dash 1, right? And 14 15 can also be combined. Tick them if they have not been ticked so far. This ticking is very important. We will see later why is this ticking so important. So 1 1 1 dash, so 1 1 1 dash, and 14 15 can be combined. So this will be the second step. Now third step would be to see the adjacent groups in this table. Now, so when I see the adjacent groups in this table, let me see if they are varying in more than one place. Yes, it is varying in more than one place. So 0 1 2 10 cannot be combined. The next combination will be 0 1 8 10. You see, they are also varying in more than one place, so they will also not be combined. Now 0 2 2 10 cannot be combined, varying in more than one place. 0 2 8 10, yes, they can be combined. Why? Because 0 is the same, dash is the same, 0 is the same, and this is the only place where it is varying. So what I'll do is I'll tick 0 2, I'll tick this 8 10, and I'll write 0 2 8 10 here. 0 2 8 10 here. And what will I write over here? I will say dash 0 dash 0. So dash 0 dash 0, right? The next, and I'll tick both of them, right? I'll tick 0 2 and 8 10. The next, I'll see 0 8 with 2 10. Yes, that can also be combined. So I can write 0 8 2 10. So it will be dash 0 dash 0, because this is the only place where it is varying. Which is not varying, will be that will be copied as such. So we are still looking for the variation in a single bit, right? So I'll write dash 0 dash 0. So this covers this particular all the combinations in these two adjacent groups. Let us now come to these two groups, their combination, if there is any. When I say 2 10 10 11, they're not combined, right? Because they are varying in more than one place. 2 10 10 14 can also not be combined because they are varying in more than one place, one bit, right? Now 8 10 10 11 cannot be combined either, right? That cannot be combined either. 8 10 10 11. Similarly, because they are varying in more than one place. Similarly, 8 10 10 14 can also not be combined. So there is no combination possible over here, right? So I'll go to the last group. I'll go to the last group. In fact, I should have drawn a line here too. Okay, I should have drawn a line. Let me do it, because that is going to give me the idea that um, this is something which is uh, I'll tell you why. Okay, so I've got it corrected. In fact, you see, these two groups cannot be combined, so I should keep a blank here, so that when I need to go beyond this step, I know that there is nothing in it, so no further combination would be possible. This is a null group, so it cannot be combined with this, it cannot be combined with this, so I'll have to stop here. So that will give me the termination point. In fact, when no group can combine, that will be the termination point. So that is why it is important that I keep a blank group here. So none of the terms here could combine with none of the terms here, so that is why a blank group. Now let us consider these two groups. So I can say that 10 11 11 15 will not combine because they are varying in more than one bit. You can see for yourself. 10 11 14 15 can combine, right? So I'll tick both of them, 10 11 and 14 15, and I'll write 10 11 14 15. And what should I write? I should write 1 dash 1 dash. So 1 dash 1 dash, right? When I say 10 14 and 11 15, yes, they can combine again. So I'll write 10 14 11 15. So 10 14 11 15 will also be combined. So, and what I'll write here, 10 14 11 15, and what I'll write here is 1 dash 1 dash. So 1 dash 1 dash. So this will be the first major step of the tabulation method. Let us take another example in the next slide and then see. Suppose in the next slide we are going to take another function of four variables again: 1, 4, 6, 7, 8, 9, 10, 11, 15. I must group them as per the number of ones in them. Since there is no zero, there is no group which has a 0 1, right? Which has no one in it. So that group remains blank. Now I'll be looking for all such minterms which have a single one. So 1 is such, so I'll write 1 with 0 0 0 1, it's binary equivalent, and 4 is another one, 0 1 0 0 with 4. So I'll take both of them. And besides them, you see 6 has 2 ones, 7 has 3 ones, 8 has 8 also has a single one in it. Okay, so let me correct this one also. Okay, so I've got it corrected. See, in the first group, I should have the minterms 1, 4, and 8, because all three of them have a single one in them, right? And I must tick them here. You see, 1, 4, and 8. And see, they are not in a sequence. So it is all the more important that you keep ticking them. So I must tick 1, 4, and 8 because they have been covered in the first group. The second group, I should look for all such minterms which have two ones in them. 6 is one of them. Tick it here and take down 6 and write 0 1 1 0. It's binary equivalent. What else? 9. 9 will be the next one because it will have 1 0 0 1 which contain two ones. So tick 9 here and take it down here. 10 will also be there. 1 0 1 0 because it has two ones. So tick 10 also. And the all the remaining, like 7 has 3 ones, 11 has also 3 ones, and 15 has 4 ones. So this group comes to a close. The next group should have 3 ones in them. So just as I said, 7 will be the first candidate. You tick it here and take it down 0 1 1 1, and then 11 will be the next one because it contains 1 0 1 1 3 ones in it. So take down 11, tick it here. So that completes this group. The last group will have only 15 in it with 4 ones, because that is the only minterm with 4 variables which has all 4 ones in it, right? So that is how I group all these minterms. Now I'll, just as in the previous example, I'll go on looking at, you know, the I'll look at the adjacent groups. So can I combine 1 6? No, I cannot combine because they are varying in more than one place. So I'll not tick them yet. When I see 1 9, yes, they can be combined, right? So I'll say 1 9, tick both 1 and 9. And what should I write? Dash, dash, 0 0 1. So I should write dash 0 0 1. 1 9 will combine, right? Similarly, why have I written 8? That means 8 has been eliminated. By 8 I mean this, they are weighted ones. 0 2 4 8, right? So 0 2 4 8. So that means the bit corresponding to the weight 8 has been eliminated. So this example also gives you an alternate way. Either I should write dash 0 0 1, or I should write 8, which means 8 has been eliminated between them. Now the next 110, no, they cannot be combined because they're varying in more than one place. Now let us start looking with 4. 4 and 6 can be combined, right? So I'll tick both of them. 4 and 6 I'll write here, and you see what will it be? 0 1 dash 0. So where is dash? Dash is at a place which has a weight 2. Remember, this is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. So basically 0, 2, 4, 8. So I can write that 2 corresponding to 2, it has been eliminated. Corresponding to the weight 2, that bit has been eliminated. So 4, 6 can be combined here. Now 4, 9 cannot be combined, varying in more than one place. Similarly, 4, 10 cannot be combined either because that is varying in more than one place. Now let us see 8, 6. 8 6 cannot be combined, varying in more than one place. Similarly, 8 9 cannot, yes, 8 9 can be combined, right? 8 9 can be combined. So I'll So I made one more correction. In fact, this line was erroneous here in between, because the same group continues, right? Now I'm after 1 9 and 4 6, after having 1 9 and 4 6, now I'll see the combination with 8. 8 6 cannot be combined, as I said, because they are varying in more than one place, but 8 9 can be combined. And the bit that gets eliminated is 2 to the power 0, which is 1, right? So 1 2 4 8. So I'll write 8 and 9, and I'll say the bit corresponding to the weight 1 is eliminated, right? Then let us see 8 10. Yes, they can also be combined. 1 0 dash 0, so this is 2. So second bit, the bit corresponding to the weight 2 will be eliminated. So that covers all the combinations here. Now I will draw a line, right? Next I'm going to see the combinations in these two groups. So can 6 7 be combined? Yes, they can be combined, and it will be 0 1 1 dash. So the first bit, the bit corresponding to the weight 1 will be eliminated, and both of them will be ticked. 6 11 cannot be combined because that is varying in more than one place. Next I'll see 9 7. 9 7 cannot be combined, varying in more than one place, but 9 11 can combine. And what gets eliminated is bit 2. So I'll tick 9 11, I'll write it here, and I'll say the bit corresponding to the weight 2 gets eliminated. Now I'll start looking with 10. 10 and 7 cannot be combined because they are varying in more than one place, but 10 11 can be combined, and the bit that gets eliminated is corresponding to the weight 1. So 10 11 corresponding to the weight 1, which in effect would be 101 dash. So either you write 101 dash, or you write the bit which gets eliminated, right? And so that covers these two, all the combinations in these two groups. Let us consider in these two groups. 7 15 can be combined. The bit that gets eliminated is the eighth one, so I'll take both of them. 11 15, the bit that gets eliminated is corresponding to 4, so 11 15 4. So, and I keep ticking. Whatever combines, I keep ticking. Whatever doesn't combine, I'll leave it there. Moving on to the next step, you see, I'll see in these two adjacent groups. 8 1 cannot be combined, right? Similarly, you see 8 2 cannot be combined. Yeah, this one can, no. Let us see 1 9 and 6 7. 1 9 and 6 7 cannot be combined. 1 9 9 11 cannot be combined. 1 9 10 11 could not be combined because they're not the same, right? So I'm looking for the same bit, right? So 8, there's no 8 here, so I'll leave it, right? Similarly 2 is only this one. The place where it has been eliminated is only this one. So now I'll have to see 4 6 9 11. Okay, but they are varying in more than one bit, so they won't combine, right? And then, okay, okay, so for your convenience sake, I have written down the terms that are eliminated, because this alone may not be helping you too much, but it what sense it makes, that I've already explained. So like when I'm combining 1 9, so it should be dash 0 0 0 1. So dash 0 0 0. 4 6, 4 6, when I'm combining, it should give me 0 1 dash 0. So 0 1 dash 0. When I'm combining 8 9, so 8 9 is giving me like 1 0 0 dash. So 1 0 0 dash. 8 10, 8 10 will give me 1 0 dash 0. So 1 0 dash 0. So that covers these two combinations. When I come here, I'm combining 6 and 7. So 6 and 7 should give me 0 1 1 dash. So 0 1 1 dash. 9 11 should give me 1 0 dash 1. So 1 0 dash 1. 10 11 should give me 1 0 1 dash. So 1 0 1 dash. Now coming these two, 7 15 gives me dash 1 1 1. So dash 1 1 1. 11 15 will give me 1 dash 1 1. So 1 dash 1. So this will be the second column. Now in the third column, we are trying to combine adjacent groups here. So when I try combining adjacent groups, I see that 1 9 6 7 cannot be combined because they're varying in more than one place. Similarly, 19911 will also not combine because they are varying in more than one place. You can see for yourself. 191011 will also not combine because they are varying in more than one place. Coming to 4667 doesn't combine, varying in more than one place. 46911, that also doesn't combine because that is varying in more than one place. 461011, that will also not combine. That is why we are not ticking. You see 19 didn't combine with anyone, so I haven't ticked here. 46 also doesn't combine with any of these, so I haven't ticked 46 either, right? So in fact nothing has been ticked so far. Now coming to 8967, cannot be combined because that is varying in more than one place. See, is varying in more than one place. 89911 cannot be combined either because they are varying in more than one place. But 8 9 10 11 does combine, right? And it combines and it leaves me with 1 0 dash dash. That is what I've written, 1 0 dash dash. And what has been eliminated is the term corresponding to the weight 1 and the term corresponding to the weight. And I'll tick both of them. 8 9 10 11 is what I'll combine. Again 8 10 will not combine with 6 7. 8 10 will combine with 9 11. So I'll tick both of them again. And what do I get? 1 0 dash dash. So 1 0 dash dash. 8 9 10 11 1 0. 8 10 10 11 doesn't combine again, right? Now looking at these two groups, nothing can be combined. 6 7 doesn't combine with 7 15. 6 7 doesn't combine with 11 15. 9 11 doesn't combine with 7 15, varying in more than one place. 9 11 doesn't combine with 11 15 either. 10 11 doesn't combine with 7 15, and 10 11 doesn't combine with 11 15. So nothing combined, so nothing in this group. Before proceeding to the next step, let us see that in 8 9 10 11 and 1 0 dash dash is effectively the same thing. So I'll cancel off 1 because we all know, x plus x is equal to x. So any minimized term, if in duplicate, can be written off. Now for moving to the next step, what all has been ticked is not of interest to us. What has not been ticked is of interest to us. Now I'll start writing what are called prime implicants. Prime implicants are those which has not been ticked here. And how will they be written? This w has been eliminated, so I'll write x dash y dash z. So in the next slide you can see my first thing is x dash y dash z dash 0 0 0 1 dash 0 0 1. You see, dash 0 0 1. What has not been in this column, all have been ticked, so I'm not taking anything from here. In this column this has not been ticked, so dash 0 0 1, so I'll take dash 0 0 1. Next, what has not been ticked is 0 1 dash 0, so I took down here 0 1 dash 0, right? This has been ticked, this has been ticked, so I'll leave them. I'm not taking them down. 0 1 1 dash, so 0 1 1 dash, right? And then dash 1 1 1. It is not minus, it is dash 1 1 1, right? So dash 1 1 1. And then 1 dash 1 1, so 1 dash 1 1. So all those who have not been ticked have been. That is why ticking is so important. If you by mistake, if you leave out on ticking anybody, even if any term, even if it combines, then you will take it down as one of the prime implicants, which will create a problem. We will see later. Again, since this could not combine and the process could not go on, so it has not been ticked, so I must take it there. So all the such terms which have not been ticked are to be taken there. So 1 0 dash dash is the last one. So once I've taken it down there, I know that 1 9 combined to eliminate 8, 4 6 combined to eliminate 2, and so on. But this is of more importance and interest to us. How can I write these? They are all the prime implicants. All those who have not been ticked are the prime implicants. So I'll write it. W gets eliminated, x dash y dash z. This will be w bar x, y gets eliminated, and z dash, right? A 0. And this will be w dash xy, z gets eliminated. This will be xyz, right? Because w gets eliminated and all three are ones. And this will be wyz, so wyz. And this will be wx bar. or wx dash, these both of them have been eliminated, wx bar, right? So they are said to be the prime implicant. So this is the prime implicant table. Next step is to find out the essential prime implicant. So what I'll do, I'll write the first term x dash y dash z and what all terms it covers. I'll write all the min terms that I had to do in the, this one. All the min terms that I had to do, I'll write there. 1, 4, 6, 7, 8, 9, 10, 11, 15. So I'll write x dash y dash z and what all it covers. It covers 1 and 9. So I'll cross here 1 and 9. They have been covered by this prime implicant. Similarly, w dash x z dash, it covers 4 and 6. It covers min terms 4 and 6. So I'll write a cross at 4 and 6 only. Next is w dash xy. So this w dash xy covers min term 6, 7. So I'll write 6 and 7 crosses corresponding to these two only. Next is xyz. So I write xyz here, and since it xyz covers 7, 15, so a cross corresponding to 7 and 15. Why I'm doing this, it will be clear shortly. Then wyz covers 11, 15, so a cross corresponding to 11, 15. Last but not the least, wx dash covers 8, 9, 10, 11. So 4 crosses, 8, 9, 10, 11. Right? Now from here, if I see column wise, I see that the min term 1 is covered by only x dash y dash z. So that is why it becomes an essential prime implicant. If I don't include it, if I don't include it, it is not going to give me a complete function because 1 will be left out. M1 will be left out. So that is why this becomes an essential prime implicant. So I'll place a tick mark here. Next, I see this column. This column also, only this is covered once, which is by this particular term. So this also becomes an essential prime implicant. This is covered by 2. So this one is not an essential prime implicant. This will not give me an essential prime implicant. 7 is again covered by 2. So this will again not give me an essential prime implicant. But 8 is covered by just 1, which is wx dash. So I'll place a tick here and it becomes an essential. Wx dash becomes an essential prime implicant. 9 has 2, so leave out. 10 has 1. 1 cross in it in the entire column. So this is an essential prime implicant, which we have already inferred anyway. This covers 2 and this covers 2. So now this gives me, out of all these prime implicants which were not ticked in the initial table, what all not ticked is called the prime implicant, and out of these prime implicant I have identified the essential prime implicants. Next, what I am going to do is I am going to either tick or encircle what all they cover. Like 1, 9 they cover, so I'll do 1 and 9 essential prime implicants first. 4, 6, so I'll tick 4, 6. So 1, 9, 4, 6 are taken care of. This covers 8, 9, 10, 11. So 8, 9, 10, 11. Now what remains is 7, 15. Which means if I write down an expression which contains this essential prime implicant plus this essential prime implicant plus this essential prime implicant, it will cover min terms 1, 4, 6, 8, 9, 10, 11. Right? Only min term that remains is 7 and 15. So these 715 will give me, these 715 can be, if they can be covered by one prime implicant, nothing like it. Else we'll have to go for 2 prime implicants, right? So if I see 715 is covered by xyz. So if I write an expression which contains 3 essential prime implicants, x dash y dash z, w dash xz dash, and wx dash, the 3 essential prime implicants, and then one which is not an essential prime implicant, but by including it I am able to cover all the terms, is xyz. So this will be my minimize function. You can say that, you might be thinking that this way xyz is also an essential prime implicant, because if you don't do it, it will not cover 715. No, I'll say xyz is not an essential prime implicant. Why? Because if I do not include x, y, z, but I include essential prime implicants, I'll have to include anyway. But if I include these two remaining ones, w dash xy and wyz, they will give me 7. 7 will be given by w dash xy, and wyz will give me 15. So even if I don't include xyz, but I do include these two, I'll be able to cover all the min terms, although that will not be a minimal function, right? Because that will add up two product terms here. But if you exclude any one of them, then all min terms will not be covered. Like if you don't include this one could not be covered. If you don't include this one, then you see which one? 4 will not be covered. If you don't include wx dash, then there is no way that you could have included 8 and 10, right? So we should be very clear about the prime implicants, the essential prime implicants, and this will be my minimize function. So again, whenever I am given a function to minimize, I must group the min terms by the number of ones in them, right? And then I try combining the adjacent groups and see what all can combine, and whatever combines, that gets ticked, very important step. And then I keep writing the whatever gets eliminated. So I can go on doing it column by column, going from column A to B, and then combining the adjacent groups in column B to get the column C. And it may continue. Since I've taken lesser number of variables, if there are more variables, it may go on to column D, it may go on to column E. That's what I said. The method remains the same, but it may become lengthier, right? So once I've got this table, what all has not been taken will be termed as prime implicants, and I'll note them turned down. And then I'll come up with the essential prime implicant table, in which I'll identify essential prime implicants. I'll write the essential prime implicants as a part of the minimize function. And whatever min terms have not been covered by the essential prime implicant, I'll try to cover them with the least number of product terms. With the least number of, which in our case was just a single one. It may be more than one. It depends on the size of the function to be minimized. Now, another thing that I must see that is this method good only for sum of product simplification? No, it can do product of simplification also. What will be the variation? The variation will be that, suppose had it been pi 146 and so on, right? So in that case, I would have been grouping them. There will be two differences. I will be grouping them with the number of zeros in them. So 0 zeros in the first group, then 1 0 in the second group, then 2 zeros in the third group, and 3 zeros, and so on, right? I'll group them in such a way, and then I'll go on combining them, right, in much the same way. So the first departure in product of sum simplification tabulation method would be to group them in as per the number of zeros in them rather than ones in it. You can correlate, you have done SOP and POS, so you can correlate why I am doing it using zeros, because POS requires doing it with zeros, right? Next departure would be when you are writing these terms, it will not be w dash x, w eliminated x dash y dash z, since it is product of some simplification. So what you will write? It will be x plus y plus z bar. When I'll go to this table, I'll write x plus y plus z bar. Some term. Similarly, this one will be w plus x dash plus z, right? This will be w plus x dash plus y dash. This will be x dash plus y dash plus z dash, and so on. So that will be the second departure. Rest of the things will remain the same. I'll identify what are the prime implicants, by what all has not been ticked, and what is essential prime implicant from here, and then try to pick up the least number of sum terms in the product of sum simplification to get your minimize function in product of sums form, right? So you can repeat the same example by taking a pi here and see for yourself whether you are able to do it or not. And you can always verify using the k-map. Do the product of sum simplification using k-map and see whether the result from tabulation method and k-map has been coming out to be the same or not. That is why I've taken four variables in it, so that you can verify with a K-map. So that is one thing. Tabulation method can be used with equal for both sum of product as well as product of sum simplification. Second, so what about don't care? If there is a don't care condition, there are a few terms which are don't care. Then how do you do them? What I'll suggest, that from the very beginning, keep treating the don't care as if they are min terms. So group the don't care conditions also as per the number of zeros or ones, whatever the case may be, product of sum or sum of product, and keep on combining them, keep on coming up, picking them, keep on coming up with these prime implicants, get all the prime implicants by treating the don't care conditions as very much the min term or the max term itself, as the case may be, in sum of product or product of sum, whatever. The difference will lie only in the last step. In the last step, when you are writing, don't write the don't care conditions here. Just write the min term or the max terms here and try identifying the essential prime. For example, there is a don't care which is covered by anyone. So that will not be an essential prime implicant now, because that is covering a don't care and not one of the main terms. So the only difference when you involve the don't care is in the last step, do not write the don't care beyond this. Before that, treat don't care as very much a part of the function itself. And in the last step, don't include the don't care condition, and then identify essential prime implicants, write down essential prime implicants, and then to it you add the minimum number of min term or the product terms or the sum terms, as the case may be, in order to complete the function. So that will be the difference when you have the don't care condition. So I'll again suggest practice using a case of a don't care. We have taken an example of don't care in one of the earlier lectures. Like we did that, BCD to 7 segment decoder in the previous lecture. So try designing all the 7 components using tabulation method now. Or you may also try, like 7 segments, try 4 segments in sum of product form and 3 segments in product of sum form, using the don't care conditions 10, 11, 12, 13, 14, 15, as we did there. So that will give you a good practice. So we will stop here. In fact, yes, before stopping, let me tell you that we have completed, takes me to the end of unit 1. So this was this is taken from the syllabus that I've shared with you already. Let us see the topics. Introduction, binary numbers, base conversions, all this we have studied, right? Octal and hexadecimal numbers, complements we have seen, r's complement, r minus 1's complement, binary codes we have seen, XS3 code, Gray code, all those, basic theorems and properties we have seen, Huntington postulates and the basic theorems, Boolean functions and representation in canonical and standard forms. Canonical sum of product, canonical product of sums. Standard form means it may not necessarily be canonical, but still it may be a sum of product or a product of sum forms. So SOP and POS forms. Other logic operations we have seen: NAND, NOR, exclusive OR, exclusive NOR. Digital logic gates. What are the gates corresponding to all these logic operations? Then function minimization. We went on to function minimization and we introduced Carnot's map. We did it for 2 variable, 3 variable, 4 variable, limitations of K-max for larger variables. So, we have seen larger variables going beyond 4, it gets difficult. 5, 6 becomes very difficult to visualize, and beyond 6, it is, impossible to do using K-map. Then POS simplification also we have seen. Take zeros in place of ones, and try combining with zeros. And also write the sum term accordingly. Then NAND NOR implementation we have seen. Sum of product and OR implementation, NAND implementation, they are the same. Similarly, POS will be OR AND implementation, and which will be equivalent to NOR implementation. We also have seen other 2-level implementations, the the degenerate forms and the non-degenerate forms. There are 16 possible combinations. 8 of them are degenerate, 8 of them are non-degenerate. So degenerate of not much importance. So how to have it in the non-degenerate forms, right? That we have seen also. Don't care conditions. We have taken a beautiful example of BC to 7 segment decoder to emphasize our point that what exactly do we mean by don't care conditions and how do we take it into account. And then tabulation method or the tabular method that we have seen today in detail, Cohen-McCluskey method. And we have seen that this is enough not just for sum of product, it can do product of sum, it can do don't care conditions also. The course outcome corresponding to this unit 1 is understand Boolean logic operation, minimization of a Boolean function and its implementation. So that takes us to the end of unit 1. From next lecture, we will start from unit 2. You are again, invited to go through all these lectures, and then if there is any problem, let me know. Thank you very much.